Hey everybody, this is Can You Tell the Truth by Lying. We're at PyData New York. It's Friday, November 8th, 2024. My name is James Powell. I give a lot of talks. I think I've spoken at every single PyData New York to date. And so of course, if you like this, you can check out any of my other talks on YouTube, or you can follow me on LinkedIn. I want to start this talk with a motivating example for telling the truth by lying. And oftentimes we can interpret this to be something much broader than communicating in our work itself. We can talk about fundamental truths of the universe, but I want to at least limit us to something more practical, more work aligned. And so it's often the case that when we're working with, especially junior programmers, we need to explain to them certain features of Python. And one thing that we may need to explain to them is some syntax that looks like this. We see this @ sign and a dec and a def f and then something underneath. And we might tell them what the name of this feature is. If we're being very precocious, we might point them at a pet to say this was introduced in such and such a version of Python. Or we might show them some use cases where this might appear, because this feature in Python appears if you're a user of something like FastAPI and you want to register a route for your FastAPI API. Or if you're a user of Python 3.0 or later and you want to do some sort of data structuring and you're tired of using the collections.name tuple, so you use a data class. Or you're a user of pandas and you say, I want to try using some advanced uses of pandas, for example, registered index accessors or registered data frame or series accessors in order to extend the capabilities of a data frame, a series, or an index. And of course, even this is quite useful because for those of you who've seen any previous talks I've given, one of the things that we like to talk about is the limitations of the pandas API, specifically that it's extremely coherently designed but incredibly inconsistent. For example, when you have an index, you have a drop level, a reorder underscore level, a sort level, a swap level. Nothing's quite spelled the same, nothing quite looks the same, and you don't have useful operations or something's missing, like there's no update level or add level. So in previous talks that I've given this year, one use case of this that I showed was you could register an index accessor that adds into the index the missing parts of pandas, so you can overcome some of the inconsistency of the API in a really easy way to grep for. You'd end up with some code that looks like this, where you can grep for like underscore x, and you can see, oh, I added this in because I'm waiting for the core pandas developers to actually catch up with filling out the rest of the details of what is an incredibly useful but very inconsistent API. But you may start with a very basic thing, and you might start with what this thing is called. You might say, well, that's a decorator. And you might give somebody a definition for this. You might say a decorator is, as we all know, a function that takes a function and returns a function. Except, that's not quite true. You might start with an example of, here's a simple decorator, and let me show you what this looks like. And if I write that decorator, or that's an application decorator, if I write that decorator, here's a decorator that doesn't really do anything. Or here's a decorator that wraps a function. Or here's a decorator that wraps a function that uses a higher order decorator from the functools module to ensure that the doc string and other details of that function line up. Or if there's a decorator like this, we can have a decorator that takes arguments, a so-called higher order decorator, and we might call this a create decorator. You can even show them an example like this where there's multiple levels, and you can overwhelm them with the mechanics of what they can do, but they still don't really know what does this even mean. You might even show them a couple of details of functional programming, things which actually came into Python later than you might think, later in the era of Python 2. Early Python 2 was much more limited than you might have expected. So you might say, this feature, this is basically a syntactical rewriting of something that looks like this, but you're going to come back to this stock phrase of, it's a function that takes a function or returns a function. Except it's not, because since this syntax is equivalent to this syntax, well, whatever the decorator is could be anything. It's not necessarily a function that takes a function or returns a function. It could be a class. This is a completely valid use of the decorator. In fact, if you think about it, this is one way that you could do things like mimic how instance method, class method, static method, or property work by, for example, taking methods in the class body, wrapping them up into a custom object, and then implementing the descriptor protocol. And in fact, for those of you who use the functools module, you've seen hashed property. You might also know that there are these additional ways in which we can customize the behavior of methods that you see in a class body. You may have even discovered that when you have a property in a class method, you have to apply them in a very specific order. This is wrong, but this is right. So you might even discover that you want to do something like a proper implementation of the class method property where the decorator that you use is not a function, it takes a function, returns a function, but something else entirely. You might even do something wild like this. This is one of my favorite examples of a very simple decorator where the thing that is doing the declaration is a data class that performs memoization by identifying that memoization is just a lookup table, and there's a very clear correspondence between a function call, the call protocol, and the get item protocol, the dictionary in this case. And here you can see a really nice implementation of it that's signature invariant, so that when you memoize this, it doesn't matter how you call this thing, which is actually better than functools.cache, which is signature dependent. In functools.cache, the second doesn't actually get cached. But you come back to your definition of a function that takes a function or returns a function, and you make it a little bit more precise. You say, oh, it's a callable that takes a function or returns a function, and that's not including these other possibilities, that's acknowledging them. Except this is not even right, because this is valid. This thing is not a function, it's a generator. Well, actually, that's not correct, because the Python interpreter says this is a function that returns a generator, but that's not how anybody talks about it. And so, the thing that comes next is not a callable that takes a function or returns a function, it's a callable that takes a function or a generator coroutine, or a generator coroutine and does some weird magic to it, or an asynchronous task, or it can appear above a class. And so it's not even a callable that takes a function and returns a function. It's a callable that operates on something defined with def or class and returns a function. Except even that's not true, because the decorator can return anything that it wants. And so you can do anything you want in the decorator body. In fact, back in the old days in Python 2, prior to, I would say, about Python 2.2, there was no real first-class functions in Python. And so there existed this function in Python in the built-ins called apply, where you give it a function object and you give it the arguments, and it would call that function object with those arguments. And so one cute trick we used to do way back in the day of Python 2 is if we had a function that returned an instance of a class, but we didn't want to make it visible, that class visible to other people to instantiate, what we would do is we would use apply to automatically instantiate the thing without ever leaving that resident in that namespace. Or another example of something like this is if you had some constant that you would compute as part of your code over some lines of code, you wanted to be careful about moving that around in your code. You'd use something like apply to have a body that would generate what the value is, but this is scoped so that you don't have other variable names leaking in and out, or you can move this around more easily. And so if we come back to our definition, what we see is a decorator is really a callable that takes or operates on something defined with def or class and returns some arbitrary value. And the question is this really better? Because when I give you this definition, you're like, what does that even mean? What are you even talking about? What can I even do with this? And you look at this definition and you're like, yeah, it's very precise. It reads like a lot of scientific papers where they're absolutely afraid to say anything that could be interpreted incorrectly. And so they end up saying almost nothing at all, or they say something that is totally and utterly incomprehensible. And when you realize that, you say, you know what? When somebody asks me what a decorator is, I'm just going to go back to the pat phrase, because you know what? It's good enough for most of their use. And when they're sophisticated enough, we can actually lead them to what the more precise answer is. Because we don't need to be writing scientific textbooks that give you the canonical, authoritative answer for these things. We need to actually help people use these tools. And this is what I mean by telling the truth by lying. It is very common that when we want to explain something to somebody, we want to tell them the truth, but we can't tell them the exact truth. So we tell them a couple of things along the way that are not truthful, that are actually lies. Like that a decorator is a function that takes a function and returns a function, which it is not. That's only in a very narrow case. Now, this is predicated on a very important detail of how we communicate with other people. Specifically, what you say is not what other people hear. You say what you think you said, and they hear what they think they heard, and there's a oftentimes humongous gap. This is a very common thing that happens to me. I have given enough talks at enough PyData events with enough hits on YouTube that it's not unusual that somebody will say, oh yeah, I came to the event last year and I saw your talk, and I really liked it. And I'll ask, oh, what was your favorite part? And what they'll tell me about the talk that I gave, I'm like, I talk about that at all? That has no relationship to what I talked about. What I said was nowhere near what you heard. And the reason for that is, when I'm writing these things, I'm paying intimate attention to every single detail. But when you're listening to these, you catch some details, you miss other details, you filter it through your own experiences, your own knowledge, you pick up on some things, it reminds you of something else, and what you hear is not what I said. Oftentimes, it's a consequence of me being a poor communicator, and oftentimes it's just a consequence of the lostness of human communication. As an aside, one thing that really weighs on me sometimes is, am I responsible for what they hear, or am I responsible for what I said? And this becomes a very complex discussion because I want the outcome of them having heard what I want them to have heard, but I also want to speak truthfully to what I want to say. And oftentimes when we go down this path philosophically, we can end up in some very odd places where I don't know there's a real answer. You might look at this and say, you're really talking about things like this Machiavellian idea of the ends justify the means, and this is a very deep debate that we simply do not have time to resolve, if it can be resolved at all. But I do want to offer you in this aside one interesting thing that I discovered when I was putting together some of these thoughts, which is this quote from Ovid, that the outcome is the test of the act. Because in Machiavelli, he never actually specifically says the ends justify the means. This is generally considered to be the source for that idea. And what you might not know is this is also the family motto for George Washington family. And the interpretation of this is also the event proves well the wisdom of her course. And you might say, this tells us some things about George Washington, his belief of the horrors of the Revolutionary War and what it accomplished. But a really interesting detail that I discovered in researching this was, the George Washington family has another family motto, which is, virtue is the only nobility. And so that really draws you away from this, the ends justify the means. It's only important what they heard, not what you said. You can lie with all you want as long as they hear the truth that you want, but instead there's some space in between here to parse this a little bit more finely. Because when I discovered this and I thought about this, I said, you know what? The truth actually matters. It matters a lot. The truth that you discover, that you want to communicate, matters even if nobody is listening, and it matters even if they didn't hear what you said. And so there's a little bit of some space in between here where we have to discover, how do we communicate this truth effectively? What do we do in order to do this? Because in truth, I am now at, I'd say 10 or 12 years of having given talks in the PyData community. And some of the talks that I've given have been very repetitive. Some of you here may have even seen some of these examples before, or some of you watching on YouTube will see this and fast forward through parts and you're like, yeah, I already seen that gimmick. And some things that I've said are things that I don't think are particularly controversial, that Pandas is a useful tool for real work, that it is an inconsistent implementation, but with a coherent design. I've tried to convince people that as amazing as tools as DuckDB and Polars are, Pandas still has a lot of place in this world to solve very specific problems. And much of the complaints that we have about Pandas is that we're maybe using it wrong, or maybe approaching it incorrectly, and may not be foundational complaints that cause us to run away from this. And I've tried to convince people that in spite of this inconsistent implementation, that nothing is quite spelled the same, that the keyword arguments are all over the place. Set axis takes an axis parameter, a rename axis takes an index equal or a columns equals parameter, that what is an index versus an axis, and still sometimes that confuses me, oh wait, the index is this one, and the axis values are this one, that sometimes you can pass in a lambda, and other times you have to go through this pipe contortion. Setting all of that aside, there's a very coherent design around some core concepts. This is the truth that I've tried to discover and try to communicate without lying to you about this is how we use Pandas. I've tried to communicate that there are core dominating concepts that allow you to use this tool, that it's a tail-end analytical tool, that it is a restricted computation domain, some sort of heterogeneous encoding, that it is organized around around index alignment. And when we talk about the tail-end analytical tool, this then leads us directly to certain consequences of how we use this tool. For example, people love to compare Pandas and SQL. When they compare Pandas and SQL, they often do this very superficially. But when you really think about it, SQL is not a tail-end analytical tool. Most SQL databases that are not in process are actually distributed computing environments that, for example, have no inherent notion of sortedness. Because in a distributed computing environment, when you're writing rows into the table, you don't know which row landed first. That could be dependent on external factors. So the sortedness of some data in an SQL table has to be stored in the data, and is always a projection in the query via a sort by. But Pandas has an inherent ordering. It has a .sort index. It has an index is monotonic increasing. The underlying data fundamentally represents some notion of sorting, because it's not a distributed tool that multiple people are writing into. It's a tail-end analytical tool that you as an individual are using to solve a specific problem in front of you, and only that one problem at that time. It's a much less generalized tool and a much more specific tool, which is why the most important thing that almost all of the previous Pandas replacement attempts fail to realize is the value of Pandas is in its modeling fidelity. Specifically, Anybody can write some group by mean restricted computation. Anybody can write some kurtosis or some skew code. We've been writing array code since Fortran's 90. But what pandas gives you is a nice balance between very, very precise modeling of what you want to model, being able to use the arbitrarily complex behavior of Python to fill in any gaps. That you can't just do a group by with certain aggregations. You can do a group by with the user-defined aggregation, and that user-defined aggregation can be any aggregation you want. And as long as you obey by the rules of group by ag, apply, transform, and the rules of index alignment, and some of the other rules that occur along the way, you're good to go. And this is why when you look at pandas, you see something very interesting, which is you have these two ends of fidelity in terms of representing pandas information on disk to CSV, which retains none of the fidelity. You can't even represent an index in a CSV file, much less any custom D types. Remember, pandas has interval data types. It has data types that have to be parsed into some sort of canonical encoding in CSV. You have to unparse them on the other side. And the mechanisms by which we even parse some of these simple things like date times have enormous complexity and slowness associated with them. And on the other side, you have perfect representational fidelity with 2-pickle, except it's too perfect that it becomes an enormous security hole. And you have all of these other tools that are sitting in the middle that allow you to do some things but don't allow you to do other things. And there's always some space where, well, hold on a second, I can't quite represent this properly. Can I put a multi-index in a Parquet file? Can I put a multi-index columns in a Parquet file? Do any of these support that? Pandas does. Pandas has the ultimate level of fidelity, and each of your data storage techniques typically have something in the middle, and then you have to have some software support to move it back and forth. Which is why it's a tail-end analytical tool. You're not supposed to have large databases of pandas objects that everybody reads from, because the only way to actually make that work with all the things that make pandas so cool is to maintain the modeling fidelity, i.e. to basically have a live coding environment of some form. And it's through this concept that we can understand some of the failings that people have with this tool. Specifically, they're using it in a way that it has not been designed to be used because they see superficial similarities, pandas group by against SQL group by. When we talk about things like the restricted computation domain, we're talking about a heterogeneous encoding, the idea that in your program, and this is something that's very interesting, perhaps not unique to Python, but unique to many of the popular languages that we use these days. There's this clear distinction between computation and program structuring, and you see it even in the data types that you use. NumPy and VArray is a computational tool. If you're not using it to represent a vector or a matrix, you're using it wrong. I have seen scientists say, why would I ever use a Python list anymore? I have the NumPy and DArray. And they put everything in NumPy and DArrays, and then it breaks on them because they have these NumPy and DArrays of PyObjects with circular references, and there's still memory leaks when you have circular references between NumPy and DArrays. And what they should realize is, when you learn about NumPy, that doesn't mean abandon everything you know about Python, but the two exist in harmony in some fashion. A list of a NumPy and DArray is a very meaningful thing in Python, the list representing the program structuring, and the NumPy and DArray representing the computation. And when you think about the restricted computation domain, this allows us to take another step back and assess the quality of alternate tools that we have. Specifically, there are tasks that are very easy to do in something like pandas that are very difficult to do in tools like SQL or polars or vice versa. For example, years ago, I gave a talk called Group-Weighted Summary Statistics. And in that talk, I showed that it's very difficult in pandas to do group-weighted summary statistics. Why? Because if you have two columns on a data frame, value and weight, you want to do a group-weighted summary statistic of high cardinality, what you're going to have to do is you're going to have to either write it as a dot apply, which is extraordinarily slow with high cardinality. High cardinality meaning you have lots of groups, meaning you're doing the UDF many, many, many times, which means you're calling it to Python many, many, many times. And if you have lots of small objects being generated by the group by apply that are then being concatenated into the final result, that index line concatenation is excruciatingly slow. So your only other choice is to do this with a decomposition of .ag, which for a group by mean type operation, a weighted mean, is fine, but try writing a grouped kurtosis using only .ag, it is a nightmare. It's like 7 lines of code, you cannot make your way through it. And it's really, really hard to do. Except a grouped kurtosis is nearly trivial to do in SQL. And when you think about some of the tools that we have and what's valuable about those tools like, for example, arrow. Well, the power of arrow is not just that it's more memory efficient, that it's faster, but the power of arrow is recognizing that in Python, when you have this heterogeneous encoding, you have things that are done with this infinite fidelity of the Python language, and with the restricted fidelity of the computational domains, pandas, polars, or duckdb. Those restricted computational domains allow some things to be encoded very easily. In SQL, a group-weighted summary statistic is utterly trivial to write. In pandas, it is a nightmare to write. But in pandas, some things are very easy to do that are very hard to do in SQL. So with arrow, what you do is the easy stuff that you can do in pandas, and the easy stuff that you can do in duckdb, and you have zero copy between them. And instead of having to fight against pandas, instead of having to fight against the tool that you have, you've all used, look, SQL has no notion of ordering, right? So if you wanted to say, give me a table of SQL and divide every value by the value of the first row, that's really hard to do in SQL. Trivial to do in pandas. But instead of having to fight these tools and to figure out how to contort yourself to encode within these restricted computation domains, with arrow, what do? You just use the tool that's good for the job, and you have zero copy between them, and you get to be very picky about this works well for this works well for that. Now, of course, I won't go into index alignment. It's a very well-trodden topic that I've talked about more than enough times, but ultimately when we think about pandas, we should think about this as a very interesting structure, something that we don't see in other data frame products. Specifically, that there's an index, and every operation we perform on pandas is index aligned in some fashion, or is obeying that index, the dynamics of this index. And there's many different mechanics behind how that index works. There's many different modalities for how that index alignment will operate, but fundamentally, when you see actual pandas code that people have, and they're getting frustrated because they're doing a reset index or dot values every other line, the answer isn't pandas is wrong. The answer might be we're using it wrong. Because we have these core concepts that dictate to us how this tool has been designed to be used and how we should use this. And in this sense, I have struggled for many, many years to convey to people that these tools are valuable, that these tools are useful, and to tell the truth. This is a very useful tool, and if you use it the right way, it will work for you very well. And if you've seen other presentations that I've given, well, one of the reasons I do live coding is because anytime I do a live coding exercise, I usually have not really worked the problem ahead of time. Because I figure if I'm actually right, if there's actually truth that I've discovered here with no tricks up my sleeve, I should be able to work a problem that I've never seen before, methodically from step A to B to C to D. And if I have to backtrack, I can backtrack using each of these concepts to say, hold on a second, I thought this, but I'm wrong because of this concept, and therefore this is what the next step should be. As opposed to how people often write their code and use their code, which is they end up going in circles over and over and over, try it, rewrite it, rewrite it, rewrite it, exhaust themselves by the fifth chance, and get through. And this leads to the live coding not only being a gimmick, but something that's useful. Fundamentally, the concepts, the truth that we have here is useful in the guidance that it gives us. But there's a very interesting aspect of this that I discovered very recently, which is, if we're talking about telling the truth to people, sharing with them the foundational truth of the way in which these tools work, or the way in which the universe in which these tools operates, and we want to do that without lying to them, without simplifying, without overwhelming them with the details on the other side, there's a huge danger of self-delusion. How do we even know we're telling the truth? Maybe we're lying to them by lying to them. And this actually happened to me the other day. As an example, I was teaching somebody about parts of Python, and I came across the concept of metaclasses, which is a concept that I've talked about many times before, that I think is something that most people view as a gimmick, but still struggle to figure out where does this actually occur in real code. And you'll see when people talk about this, the same sort of pat answers that we get when people talk about, say, decorators. Things like an instance is to a class, as a class is to a metaclass. Or you even see things like these analogies put into use in simple examples like, if we have some class of some type, and we create an instance of it, and we call this thing, in this sense of calling, type object call, not exactly, because certain TP methods are accessed via direct struct lookup and other ones aren't, but this is a close enough simplification. See, that qualification there wasn't useful at all, but I felt obligated to do it in order to tell you the truth. Was I telling you the truth, or was I overwhelming with things? But whatever the case may be, they show you something like this, and they say, okay, we have some code that looks like this, and when you have this call here, it is implemented via this call, call. But if you look at this code again, you can see there's this call, there's this open close parentheses, and that's actually where the meta class comes in. If you want to implement the Python vocabulary not on instances of classes, but on classes themselves, that's where meta classes come in. So if you want to write something like this. But this ends up being overly mechanical, and we're following the same track that we had before of overwhelming people with the details and obscuring what they actually want to do. We might be telling them the truth, but they're not hearing the truth of what we're trying to accomplish. They're getting lost in all of these details. And the details are interesting, and they're approachable, and perhaps even acceptable by a certain level of audience. But for the majority of the audience, all of this is just over their head, and they've maybe been wowed, but they haven't really heard what you wanted to say. And so when you talk about these things, maybe we try to do a reframe. And when I've talked about meta classes, I've tried very hard to reframe them away from the mechanical example. To say this is not a head-exploding, mind-blowing thing, but it's a very, very simple use case that you can really feel in your life. For example, you're writing some code and you're sharing with somebody else. And there's a library, and there's a user. And the library defines a class, and the user uses that class. And in the library, the class that is defined has some method. And in the user.py, the class that's used, that's derived from, needs to use that method. And if you exist on the bottom side of the screen, then you're kind of worried if people on the top side of the screen do something wrong. If they delete that method f, your code breaks. But it's almost trivial for you to make sure that doesn't happen. One way you can do that is unit test, another way is you just assert the presence of this attribute. In other words, a very real thing that we've all lived through. We're sharing code with somebody else. We're providing a library to them. They're using that library. And that person wants to make sure that we don't make a change that blows them out. So what do? Well, there's a million things they can do. There's all sorts of things they can do. There's so many techniques to do this because fundamentally in this example, the library user can see the code they're using. But when we find ourselves on the other side of this, we're writing a library and somebody's using it. We want to make sure they use it correctly. And we don't know that they're using it. We don't know that they exist. Their code doesn't exist at the same time that our code exists. What can we do? In fact, this seems like an almost intractable problem. How do we enforce constraints on our users if we don't even know who our users are? And when you think about that, that's a very common, very livable experience. You've distributed some code to somebody. You want them to use it, but you want them to use it in a very constrained way. In terms of, for example, ensuring that certain methods that they write that you want them to write are implemented. And before you tell me about nonsense like the ABC module or the Python standard library, which is honestly not even really worth using because it's overly specified, we can talk about what the mechanics actually are. And there are 4 ways to accomplish this goal. For example, you can use build class from the built-ins, which allows you to intercept all class construction throughout the program from the time when you overwrite this. But this is not a very surgical approach. This isn't even a broadsword. This is a nuclear bomb. This thing affects every class construction that occurs throughout the entire program. It's nearly useless because you'll never be able to you will be able to narrowly target sort of maybe the thing that you want to enforce the constraints on, but the blast radius will be enormous. And you don't quite intercept in the right point of this, and nobody even knows that build class exists in the first place. So other than like debugging your instrumentation, forget it. This is not something you can actually do. Then you can show somebody what a meta class is. And you can say, well, meta classes are actually inherited down the object hierarchy, so we can write a meta class, we can implement new on that, and anytime somebody derived from meta class, we can check in the meta class new, they've actually done that derivation correctly. And that's how something like ABC works, except the problem is ABC doesn't really check the things that you want to check, and it protects against things that don't really happen very often, and so it ends up being both too general and too specific. But the other problem with meta classes is they're kind of weird, and nobody really likes to use them, and they have some weird things where you have meta class conflicts, and everybody feels very intimidated by them. So you show people init subclass, introduced in Python 3.6, a very easy way to solve this problem. In your base class, write an init subclass, in the body of that init subclass, you can do any sort of checking you want when somebody initializes a subclass. Or you write a class decorator. And in that class decorator, you do any check you want. And so you give somebody some code, and you say, inherit from my thing that is an init subclass, or use my class decorator, and that's the way that you enforce those constraints. And when you look at the variety of options here, you can say, well, there's some decision making that we might make. If I want to cheat you, if I want to show you the truth of what this accomplishes, I can say, well, the truth is build class is very obscure, and it's kind of hard to use. Meta classes are less obscure, and they're also kind of hard to use. Init subclass is kind of new, so most people don't know about it, even though Python 3.6 was introduced about 10 years ago, but it's really easy to use. Class decorators, they're a little different. people don't usually think in terms of providing library code in the form of class decorators. The data classes module is probably the first part of the Python standard library that really tried this approach, but they're very easy to use. Or you can frame this another way. That build class is useful for debugging. That meta class is the old way of doing things. That hidden subclass is a new way of doing things. That decorator is just another way of doing things. Or the traditional way that I have until just last week introduced this is build class and meta class operate on a partially constructed type or operate on a pre-constructed type. Init subclass and decorator operate on a fully constructed type, which means there's certain things you can check in some cases and things you can't check in other cases. For example, the meta class is the only way, the meta class and the build class are the only ways you can check that code existed in the class body, not came into being sometime after the class definition, but before the decorator. You could even talk about the affirmativeness of these approaches. Build class is automatic. Nobody even has to know it exists. In fact, there could be build class overrides in your code you wouldn't even know because it's not really visible to anybody. Whereas meta class new is a little bit manual. You have to do a subclass relationship. In its subclass, you have to do a subclass relationship. Decorators, you actually have to apply that decorator. You have to choose to do something in order to do something. But recently, in trying to investigate the truth of this, I was dissatisfied by this answer because I was like, these are very mechanical things, and I have a really nice story for when you want to use them. And I feel I can convey that story truthfully without eliding the details by telling you a story about how your life might be lived. You have this problem with your users and you want to solve this problem. You give them some code, they use it poorly, it breaks, they blame you, so you want to figure out ways to make sure it doesn't break for them. And the way you answer this is you can look at the signatures for these. And looking at the signatures for these, you can identify that there's actually a nice timing here where these occur at different areas in the scope of this. And you can discover that you don't have to lie to people to tell them the truth. You can tell them exact truths. You don't have to simplify everything in order to express to them something that's true, and you also don't have to go overwhelming with the details of all little nuances. What you can do is you can find livable examples, personal examples, things which they can intuit, and you can say, in this circumstance, this might happen. You'll encounter this. These are the qualifications how you might use that. There's a lot of truth behind this. And when you come to things like decorators and you're trying to explain it to them, you can say, well, decorator is something that you might use if every time you're writing a function, you do a common thing. Register it, wrap it, do something else. But likely, you're just going to tell them it's a function that takes a function, returns a function, and say, ask me if you have any questions. This has been Can You Tell the Truth by Lying? I'm James Powell. Thank you very much.